Hello there. In this video, I want to talk very generally about how to formulate equations of motion with Newton's second law. And for the duration of this video, we're not going to be including discussions of rotation, and we're going to be assuming that we're talking about equations of motion in an inertial frame. Okay? So what's kind of the basic goal of mechanics if we think about it at a very high kind of level? Right? So let's say here that I have a system of rigid bodies, okay? And each rigid body has a center of mass that I'm kind of labeling in blue here, and maybe some of them are free to move around, and some of them have constraints on them, which I'm kind of indicating with these dashed lines. Maybe there's some kind of constraints that are restricting the motion of some of our rigid bodies. Right? And if this is a dynamics problem and all of these, rigid bodies are moving around, I need to define a set of coordinates Q, okay, in order to describe the location of all of these rigid bodies. So these are, these are Cartesian coordinates, x's, y's, and z's, or, angles, theta, or radial distances r, right? Right, so I just wrote out here that Q, this is an n-tuple, it's just a big list which contains all of my coordinates that I need to describe the locations of every rigid body in my system. Right, and because Q is very much just a general set of coordinates depending on the problem that we're talking about, right, we call this Q, we call this very naturally a set of generalized coordinates. Right, but here's the point, is that if you give me, right, for this system, let's say that you give me an initial set of coordinates, Q naught, right, and these are the initial coordinates at some, initial time t equals t naught, right, okay, and it turns out you also have to give me information about the generalized velocities at t is equal to t naught. But anyway, so you tell me where all of my objects are at t equals t naught, and you tell me what their generalized velocities are at t equals t naught. But if you give me that initial information, and I'm able to use some physical laws, right, some set of physical laws to come up with q as a function of time, I've won the game. Because now I'm able to tell you the location of every rigid body at every moment in time. That's so powerful. And not only that, I can also go through and I can calculate, generalized velocities by taking a time derivative, right? I can figure out the velocities of all of my objects at any given moment in time. Maybe then I could derive other measurable properties from these, like maybe the kinetic energy of my system as a function of time, right? But you can see though that if I get this function here describing the coordinates of every object in my system at every point in time, we've won, right? Victory, good for us. Alright, so let's go ahead and start going through this step-by-step recipe in order to do what we just discussed. Right, and so for each of these steps, I'm going to work them out for a very trivial example here on the left as well, just dropping a ball, right? But if the main goal is to figure out how our generalized set of coordinates is evolving through time, right? Well, the first step is we need to figure out how many coordinates actually are necessary to describe our system. How many coordinates do we need? So we can find the minimum number of coordinates necessary to describe our system, or the degrees of freedom, with this equation here. D is equal to 3n minus c. And c refers to the number of holonomic constraints. Ooh, that's a fancy word, holonomic. What does that mean? That means I can express the constraint in the following way. F of q, t is equal to 0, right? And what this allows me to do is this reduces the number of independent variables, right? Just really simple example. Let's say that I was using Cartesian coordinates and my holonomic constraint looks like x plus y plus z is equal to 0. Then immediately from this, I'd be able to say, look, x is equal to minus y minus z, right? Or in other words, x is dependent on y and z, okay? And so we can see that this leads to a reduction in the number of coordinates that we need. Because if I just give you y and z, you'd always be able to tell me what x is. Okay, but math aside, a lot of this calculating degrees of freedom stuff usually just ends up, following intuition, right? Before we even define the coordinates, we can usually think about the degrees of freedom. So for example, in this dropping a ball situation, okay, I know that n is going to be equal to 1 because I just have one rigid body. So 3 times 1. And first off, it's restricted. I'm not even defining coordinates here. But we know if I'm just dropping it, right, it's restricted to this line, right, just up and down, okay? So in other words, I get rid of the fact it can't move left and right, and it can't move in and out of the page. So I have minus 2, right? Really, I have 2 constraints. I'm saying you can't move this way and you can't move this way. You can only move up and down, right? And so this is going to equal 1 degree of freedom. Right? But the key is, now I know that I only need 1 coordinate to fully describe this system. Alright, so this brings me to step 2. Now we have to actually choose our coordinates that we should track. Alright, and as a general rule of thumb, right, a general guiding principle, typically these coordinates should make our constraints, very easy to write out. Okay, and I went ahead and wrote out like 5 of what I consider to be the key kind of coordinate systems that you can usually use to tackle a problem, okay? So those are the Cartesian coordinates, polar coordinates, spherical coordinates, cylindrical coordinates, or, you might have to define a more abstract coordinate system. Okay, so for this dropping a ball problem, right? We have to always, you have to put an origin in your coordinate system down somewhere. But of course, we should use Cartesian coordinates here, right? Because if I use Cartesian coordinates, call this x, y, and z, right? Then kind of it's very easy to express my constraints, right? If this ball is just dropping, along this z-axis, then x equals 0, y equals 0, right? Here are my 2 constraints, and we can see that this is consistent with, the definition of a holonomic constraint, right? So those are my 2 constraints, and so the only parameter that can vary, what the coordinate that we're going to track, is going to be z. Alright, so next we're on step 3. So for step 3, we want to collect the position vectors Ri, right? And the net external force vectors Fi, right? For each ith body in terms of your coordinates, right? A bit of emphasis here. I'm not calling this Qi. This is not just the list of coordinates that are necessary to describe the position of the ith body. We need a position vector in terms of our coordinates. Those are 2 very different things. So for this dropping a ball example, I'm going to dedicate 1 picture to figuring out Ri, which is really, we just have 1 body, so just R, and then I'm going to, dedicate 1 picture to F. So for each picture, the first thing that we need to do, we're talking about vectors, right? So we need to define some basis vectors. So I'm just going to go ahead and define, my unit vector z hat. So we have the z hat direction, right? And in which case, we just point to our, our center of mass of this ball with a position vector, should be straight down. It's not drawn perfectly. R, right? In which case, R is very clearly just going to, it's going to have some component z in the z hat direction, and of course the sign of z, right? Maybe we're tempted to put a minus sign here because we see this vector is pointing down. Of course, if the ball starts up here, we would have a positive z, and as it drops down, right, it'll get that minus z. The point is that this z will take on that positive or negative value depending on where the ball's at. So we don't put a sign there. Alright, and then in this bottom picture, I'm going to make a free body diagram. We can go ahead and label the center of mass of our ball here. And remember, all external forces we draw acting from our object's center of mass, because that's what net external forces do for an arbitrary system of particles. They accelerate the center of mass point. So I'm going to go ahead and draw out. We have some force vector mg due to gravity, right? And of course, we can see that this is going to have some magnitude mg, and it's going to act in the minus z hat direction. Or we just have minus mg z hat. All right, and then for step 4, we're going to write out Newton's second law. Fi equals mi times the acceleration ri double dot for each body. And then we're going to apply our necessary constraints, and from Newton's second law, we're going to extract out equations of motion for our coordinate. Okay, so for this dropping a ball example, right? So we have our position vector r, right? But we need to differentiate that twice to get r double dot, right? But of course, this is a very trivial, time derivative. So in other words, r double dot is just going to be z double dot in the z hat direction. That's what makes working with Cartesian coordinates, very convenient also. But again, for other coordinate systems, this might not just be a trivial, derivative. This could be a slightly messier derivative that's more involved and also more insightful about our given coordinate system. All right, but for this problem, let's go ahead and write out F equals ma. So we have minus mg in the z hat direction equals m times z double dot in the z hat direction. Okay, and we cancel this, and check out where we're at. So we're at minus g z hat equals z double dot z hat. All right, and we don't really have any more constraints to apply, so we're good to go on that front. Okay, but then from this, we're going to pull out, right, our equation of motion for our z coordinate. So z double dot equals minus g, right? Hopefully I'm making this idea super clear, that we're using Newton's second law, which is vectorial in nature, okay? And then with this vector-based equation, we're then pulling out equations of motion for our coordinates. All right, on to step 5. Okay, so we have our equations of motion for our system. If these are simple differential equations, great. Let's just go ahead and solve the equations of motion by hand for a set of initial conditions, Q naught and, Q naught dot. And we can find our, function of our coordinates as functions of time, and we win. If our system is too complicated, though, that's okay. We don't need to give up, right? We can still solve the system numerically with a computer, for example. We could also analyze the differential equations, to come up with useful stuff. We could find its like equilibrium points, check if we have stable or unstable equilibrium points. We could take limits or Taylor approximations. We could analyze and ask questions like, do we have a chaotic system? I don't want to go through and define all of these things rigorously in this video. I could dedicate other videos to exploring such ideas. But the point is, we don't have to give up if we can't solve, our set of differential equations by hand. There's a lot of stuff we can do. Okay, but in our example here, of course, we have a very simple differential equation. Okay, so we can just go ahead and solve this. I just went ahead and proposed some initial conditions. We say our ball is at some initial height, z naught, and that we throw it with, 0 initial velocity. So we're not even really throwing it. We're literally just dropping it, right? We're not giving any initial velocity to the ball. Okay, so how do we solve this thing? Well, of course, this is a very simple differential equation. So z double dot equals minus g. We literally just integrate this twice. So the first integration is going to give us minus, right, gt plus c1. Second integration is going to give us minus 1/2 gt squared plus c1t plus another constant c2, right? And next we go ahead and we apply these initial conditions. Okay, so if z dot at t equals 0, that's this guy here. This is really equal to z dot, right? So this equals 0 when t is equal to 0. So this equals minus g times 0 plus c1. Okay, conclusion 1, right? c1 C1 goes to 0. So C1 is definitely going to drop out. So then next we go ahead and we apply this initial condition here. So we have already that C1 is going to 0 out. So next, Z at t equals 0 is equal to Z naught, which equals minus 1/2 G times 0 squared plus C2. And we can immediately see here that C2 is equal to Z naught. So in other words, our equation of motion, Z as a function of time, is Z naught minus 1/2 GT squared. Beautiful. Alright, and in future Newton's second law videos on this channel, I'm going to try and adhere very closely to this 5-step program, this little recipe that we have here. So hopefully this is a very clear and logical approach in order to tackle basically any Newton's law type of problem. And I'm going to practice these steps on this channel for a while, and then eventually we're going to incorporate rotation and, we'll think about non-inertial frames, and then we'll update this recipe, okay? If you enjoyed this video, let me know in the comments below and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.